So we're going to have a bunch of spotlights and one oral. And everybody please sit down. We don't want to violate any fire codes or anything. I was told I had to say this before the session started. Okay, so the first spotlight is going to be Learning with SGD and Random Features by Luigi Caratino, Alessandro Rudi, and Lorenzo Rosasco.
Okay, so hi everybody. I'm Luigi Caratino, and this is going to be a joint work with Alessandro Rudi and Lorenzo Rosasco. We're going to be dealing with a classical supervised learning problem where given a set of endpoints x and y's, what I want is to learn a nonlinear function f, which is, for example, defined by a linear combination on some nonlinear features. And what I would like is to learn this function here in a computational efficient way. And I would like this function to be provably accurate, meaning that it's going to perform well on future data and has a low test error. So we're going to combine two main ideas to solve this problem here. The first one is that we're going to learn the weights of our function through stochastic gradient descent. And the second one is that the nonlinear features are actually going to be random features, so which are defined by some random sketching followed by nonlinear function. And the algorithm that we are actually going to consider is stochastic gradient descent with mini-batching, which means that we're not going to consider only at each iteration the gradient with respect to one point, but with respect to a batch of point B. I also want you to notice that we are not using any explicit regularization terms for this iterative method here. And another thing that you see is that we have a few free parameters, which are the step size, the batch size, the number of random features, and the number of iterations that we are going to run our algorithm. So the computational complexity of this algorithm here depends on all these algorithmic choices. And so the question that follows is, so how do we choose this parameter here in order to reach a low test error? So one of our main results states that choosing the squared loss, we can control the test error. In details, we are going to control the excess risk, which is the distance between the error of the function that I've learned and the error of the best possible function that I could have learned. So I can control this quantity with a value that depends on all the parameters of the algorithm, so the step size, the batch size, the number of random features, and the number of iterations. So what I see is that all these algorithmic choices play somehow an implicit regularization role. And so now what I would like is to find some good values of these parameters here that allows us to reach the best possible learning rates. And in this work, we give a sort of receipt of different possible choices for these parameters here. So I'm now going to give you a couple of them. So first, I'm going to start telling you that under just some basic assumption, I know that I can reach a learning rate of 1 over square root of n. And the first thing that I want you to notice is that if we consider just a vanilla stochastic gradient descent one pass, I can take a step size of 1 over square root of n. And I'm just going to need a number of random features which are of the order of square root of n, which is much lower with respect to some previous results. And if instead I want to use mini batching, what I can do is take a batch size of square root of n, and I'm going to be able to reach my desired goal in one pass and take a constant step size this time. So now my algorithm has a computational complexity of n square root of n in time and square root of n in space. And I want you to notice that these are these values are both factor square root of n better with respect to stochastic gradient descent without random features, or random features but in a different setting like regularized kernel ridge regression. What I see is that Also in practice, we can recover all the things that we observed in theory, so that a number of random features of the order of square root of n is enough to reach optimal accuracy, and also that all the other relationships are preserved between step size, batch size, and number of iteration. So to wrap up, the stochastic gradient with random features algorithm leads to optimal accuracy with just a minimum number of computations. In this work, we also give you how to reach faster rates under more refined assumption and how to use a more general decreasing step size. And if you have questions and wants to know more on how to choose the parameter the best way for other scenarios like multiple pass cases, just pass by poster 127. Thank you.
Thank you. The next one's going to be Kong, Kernels for Ordered Neighborhood Graphs by Moaz Drayev, Konstantin Kutskov, Kevin Skayman, and Milan Vojnovic.
So hello everyone, I'm Kevin Skayman, and this is joint work with Moaz Drayev from Huawei Noah's Ark and Konstantin Kutskov and Milan Vojnovic from London School of Economics. So the purpose of this work is to design scalable, flexible, and efficient graph representations that we can then use for any machine learning task, whether classification, clustering, or regression. And I'm sure you all know that graphs are extremely high-dimensional objects, and they're very difficult to characterize and to capture into just a single vector representation. You have many relevant features for these graphs. I just listed a few, but there are lots of others. And in our work, we would like to also capture an additional information, which is that we have an order on the neighborhoods of each node. So if you think about, for example, friends on a social network, if you have 500 friends on a social network, I'm sure they are not all as important as one another. And this added information, which is sometimes available in your data set, we try to capture it. Another example is if you have a dynamic graph, so the edges are going to be created in a certain order, and we will use this information. So what we propose is a framework for creating graph representations, which is based on 4 steps. The first one is that we use an iterative procedure for representing each node of the network. This can be used, is quite flexible. We have a lot of different types of procedures that we can use for this, including Weisfeller-Lehmann and breadth-first search. Second, we're going to use a string kernel to represent each node. So each node we have a string representation, and we rely on the k-gram counting approach. Third, we can improve the power of these kinds of representations using polynomial or cosine kernels. And finally, maybe the more important part is that we use a sketching method to approximate these very large dimensional representations in order to have something which is scalable. Okay, so just to have a visual representation of all this, we start with a node, with a graph. For example, you have a graph of 6 nodes here with string representations for each of these nodes. And the idea is that we are going to create the sketching representation on the fly during the iterative process. So here you have 6 different sketching representations, and all these are going to be just d-dimensional vector, and you can assume d is relatively small. Then during the iterative scheme, we're going to aggregate string representations of each neighbor. And you can see, for example, node 1 is going to aggregate his neighbor's representation, which is A, and you're going to use this kind of iterative approach. And at the same time, you update also the sketch representation. So you can see clearly here that the good advantage of this is that while the string representation is going to scale exponentially in the number of iterations, the sketching representation remains small. One of the good advantages is that this creates scalable representation, and you can have a lot of different iterations on these algorithms so that you can represent the more complex structure of the network. Okay, and finally, once you have node representations, you just have to aggregate them in a simple way. What we do is just take a sum of all these node representations to have a graph representation. So a very simple method. Okay, so just to summarize, there is a lot that I hid under the hood, but please come and see us at our poster, number 122. The idea is that we try to design a scalable, flexible, and efficient graph representation, and maybe one of the main aspects of this is that this is a vector representation as output, which means that you can use it for whatever machine learning task that you want, or plug it into any type of clustering or classification algorithm. Thank you very much.
Our next spotlight is quadrature-based features for kernel approximation by Marina Monhueva, Yermek Kupchev, Evgeny Burnaev, and Ivan Oselidets.
Hello everyone, I'm Marina and I'm presenting quadrature-based features for kernel approximation. This is a joint work with Yermek, Evgeny, and Ivan. We developed a new method to approximate feature maps. And let me first brush up kernel methods for you quickly. So the key concept here is the kernel trick. The kernel function allows you to compute similarity or distance, which I really like, in the implicit Hilbert space using given feature input space. For example, using a Gaussian kernel, you can map these two concentric circles into feature space where they can be linearly separated by a hyperplane. However, I would think twice before applying them directly to real-world large-scale datasets because these methods scale poorly with the number of samples. You can actually avoid often restrictive training time by reverting the trick and using approximate feature map, obtaining a new representation and plugging it in linear methods, and voila, it yields comparable performance. But how do we generate approximate mappings? Popular random features methods use integral representation of the kernel. In our work, we consider kernels with Gaussian weight, and among such kernels, there are shift invariant and pointwise nonlinear Gaussian kernels. Random Fourier features mapping uses a transformation of nonlinear functions like cosine and sine stacked on top of a random linear one. And it is easy to see that random Fourier features are equivalent to Monte Carlo approximation of the integral. Recently, some extensions of the method have been proposed, such as orthogonal random features, and they use more clever points for better accuracy and faster mapping. We develop a method that uses smarter quadrature rules, which is a numerical integration technique. For this, we need to change to the polar form of the integral and apply radial rules for the radial region of the integration, and similarly spherical rules for the spherical region. Okay. Combining these spherical and radial rules, we arrive at a very efficient but somewhat forgotten, for some reason, integration technique, which is called spherical radial rules. You can control the accuracy of approximation by choosing the degree of the rules, and when you pick degree free and free, like on the slide, the formula for the rule kind of blows up, but it's still comprehensible and easy to code. The integral of the kernel can then be estimated unbiasedly by averaging the rules. And in our paper, we also derive the error bounds for the method. Obviously, when you use greater degrees, the formula gets even more ugly. But what happens when we use lower degrees? It turns out that the spherical radial rules of degree 1 and 1 generalize random Fourier features. Meanwhile, orthogonal random features are exactly as our rules of degree 1 and 3. We can also make the mapping faster with orthogonal butterfly matrices, which are dense, but they have nice and sparse structure in their factors. Now you can see the performance in terms of kernel approximation accuracy, and our method yields the lowest error possible. In short, our method is applicable to a wide range of kernels, uses structured matrices, achieves high accuracy, and generalizes previous work. Thank you for your attention, and you're welcome to check out our poster 130 today.
Our next spotlight is Statistical and Computational Trade-offs in Kernel K-means by Daniele Calandriello and Lorenzo Rosasco.
Hello, I'm Daniele Calandriello, and this is joint work with Lorenzo Rosasco. There are many ways to define the K-means problem, but for the sake of this talk, let's just say you have n points, and you want to cluster them into K cluster, so that points inside the same cluster are very similar to each other, and points across cluster that are not very similar. For this, there are a multitude of algorithms. The most popular ones are iterative, like Lloyd's algorithm with smart initialization, like K-means++, but they all hit the same limit. The fact that as long as you use linear distance, you're going to only find linear separation. And when your data is shaped non-linearly, like in this example, your K-means problem is going to settle for a very suboptimal separation that doesn't really separate anything. That's why researchers came up with kernel K-means, where the core idea is you're going to take your data and map it using a feature map phi into a higher dimensional space, hoping that using this nonlinear mapping, things become nicely separate. For example, I can add a third nonlinear feature, or let's say third dimension, that measure the distance from the origin, and then now the points in the inner circle that are closer to the origin are nicely separated from the points that are far away from the origin. Now, this is not clear how to do this when your projected space becomes very complicated, large number of features, but luckily you can just rewrite the whole formula in terms of distances, and distances in terms of similarity. And in practice, what you do, you're just going to replace your linear similarity with this nonlinear similarity K, which is just a kernel. And computation-wise, you're just going to build as a data structure a big similarity matrix that contains all the similarity between your points. The downside is this is clearly non-scalable because it takes n squared time and space to construct it, and your iterative method has to transverse it once at every iteration, which is even heavier. That's why people decided to try to approximate this feature map phi with some parametric approximation phi of m, which in our case is just going to correspond to approximating the kernel with a Nystrom approximation of the kernel. It's a bit complicated to explain in terms of kernel, so I'm just going to explain the algorithm. You take the similarity matrix and you just subsample uniformly at random m columns. And that's all the data that you're going to store in memory. And then your space reduces from n squared to nm, so a huge improvement. And each iteration is just going to take nm time to transverse it. And the question naturally becomes, I can get grid speed up by only computing a subset of my metrics, but that's going to lose accuracy, because now I'm not computing a lot of the similarities. So how big should I take this uniform subset to maintain accuracy and get a good solution? And to ask ourselves this question, we have to look also at the statistical aspects of the problem, not only at the computational. And to talk about statistics, we first have to add some assumption. We say our points are going to come from a distribution mu, so that we can design a test error, which is the thing that we really want to minimize. Because while we find the optimum on an empirical error, we would like our cluster to well separate the data also in expectation on future data. And our main result is to show that this test error is going to be controlled by two quantities. The first one scales like 1 over square root of n, and it's a statistical error that comes from the fact that you're minimizing the cost function over a bunch of points instead of over the whole distribution. And it's kind of a lower bound of what you can achieve. And the second one, which is the interesting new part, is that your error when you use only m columns instead of the whole matrix is going to scale like 1 over m. And it's easy to see that you can balance these two errors by only selecting a small subset of your matrix, only square root of n columns, and still obtain optimal rate. This gives you a huge speed up. Essentially, you go from n squared to n square root of n space and time, but you maintain essentially the same statistical error. And it's also a huge improvement over previous bound that essentially required the number of columns to be all of the matrix. And of course, people were doing this in practice for a long time, and they already saw that After, when you plot test error over your embedding size beyond a certain amount of columns kept, you had no real improvement. It's just that now we know where that point is. So to wrap it up, we have improved bounds for the statistical versus computational trade-off in k-means and kernel k-means. Note that this applies also for traditional k-means where the number of your dimensions in your Euclidean space are larger than your dataset. Think RMI in medicine. And it's also the first result where you can provably show that you can save computation without losing accuracy. The result I showed you are for the true minimizer of the k-means problem, but we have similar result for the k-means plus minimizer, which can be computed efficiently. And we also have a bunch of conjecture and open question. For example, if you can achieve fast rate, which can be done from the approximation point of view, but there are no statistical results for fast rate for k-means currently. So if you have any suggestion on how to do this, I would welcome you at my poster. Thank you.
The next one is going to be an oral, and it is a neuroscience work, and it's integrated accounts of behavioral and neuroimaging data using flexible recurrent neural network models by Amir Desfouli, Richard Morris, Fabio Ramos, Peter Dayan, and Bernard Baleni. And I believe Amir is the one presenting. So we'll have about 2 minutes of questions at the end. So prepare questions to ask.
Hello everyone, my name is Amir. I'm from Data 61. I'm going to talk about how we can use recurrent neural networks for the analysis of neuroimaging and behavioral data. We study how brain makes decisions. It's a system in the brain that enables us to learn from our past experiences and make future choices. And it's important to understand how this system works because it's related to many kinds of psychiatric and neurological disorders. Typically, in the studies of neuroscience of decision-making system in the brain, we collect 2 kinds of data. The first kind of data is behavioral data, in which we ask a human subject to complete a decision-making task. In this case, we ask subjects to complete a 2-armed bandit task. They had a choice between making an isocut toward this red circle here, or to press a button with their right hand. And after a while, they received the outcome of their choice, which is either a monetary reward or no reward. Subjects completed around 300 trials of this type, and we recorded their behavior, which can be summarized as the actions of the subjects, the reward they have received, and the state of the environment when they were making decisions. This can be thought as the output of a decision-making system. At the same time that subjects were making choices, we also recorded their brain activities using an MRI scanner. MRI scanner takes 3D images of the brain at regular intervals, for example, every 3 seconds or every 1 TR shown here. And each image represents the activity of each voxel in the brain at the time of image acquisition. Voxels are shown by squares in this graph, and if we put all the images together, we will get a time series for the activity of each voxel of the brain during decision making. So the neural data can be summarized as the activity of each voxel at each point in time for each subject. Given these 2 sources of the information, one of them is about the output of a decision-making system, and the other one is about the mechanism. We want to have a computational model that can explain subjects' behavior using the same mechanism that the brain is using for making choices. A previous approach to this problem has been using model-based fMRI analysis. In this approach, we fit a computational model, typically a model from reinforcement learning family, to the choices of the subjects. In the next step, we simulate the model in the task and we record the internal signals of the model. For example, the values that the model is tracking for each action. Finally, we regress those signals against the activity of the voxels in the brain in order to find out which brain region is encoding which part of the computational model. This has been a very influential and interesting approach. However, as a limitation, as you see, the model is only fitted to the behavior of the subjects. The model is totally blind to what's happening in the brain. Even if the model can produce actions which are similar to subjects, the internal signals and the statistics that the brain is tracking might be different from the ones that the model is tracking. In this case, there will be regions in the brain that are involved in reward processing and decision making, but they will not correspond to any internal signal in the model, and they will be simply missed in the analysis. To overcome this limitation, this is a model that we have suggested. It has a recurrent neural network layer which receives a past action, reward, and a state of the environment as inputs. And then through a softmax layer, it makes predictions for what would be the next action that the subject will take. We then compare that action with the actual action the subject chose in the task, and we build a behavioral loss function based on that. This can be thought as a form of meta-learning or learning to learn, in which the model learns to learn how humans learn in the task. But we also wanted the model to learn to use a similar mechanism as a brain for learning in the task. We want the activity of the model to be similar to the activity of the brain. For that, we connected the output of the RNN layer to each voxel in the brain through a linear layer here. In this way, we are encouraging the model to track the information and the statistics that are useful for explaining and predicting the activities of the voxels in the brain at each point in time. And then we compared those predicted activities with the actual recorded ones and built this neural loss function. Finally, we combined these two loss functions using this hyperparameter lambda that we set using cross-validation to make this final combined loss function that we use for training the whole model. Ideally, in this way, it will have a computational model that can characterize subjects' behavior using the same mechanism that the brain is using for making choices. But then how we can use this model, how we can interpret this model. Here I'm going to show how we can use this technique for tracing the flow of the reward information in the brain. Let's say there was a choice point here, and subjects made a choice, and they received the reward as a consequence of that at time t1, and then later on in the task, at time t2, there's another choice point here. First question is, how much reward feedback received here will affect the choice here? We can directly calculate that based on the gradient of the policy at time t2 with respect to the amount of reward at time t1. This will tell us how much the reward received at time t1 will affect the choice at time t2. But then, for the effect of reward to reach from t1 to t2, it has to pass through the medium of the brain. The reward travels to different brain regions, being processed by them, and then comes out as a choice at t2. Can we recover those brain regions? Let's say at time t, I want to know what's the contribution of this certain voxel in transferring the effect of reward from t1 to t2. We can first ask how much the activity of this voxel is affected by the magnitude of the reward here. That would be the gradient of the voxel activity with respect to the amount of reward here. We can then ask how much the activity of this voxel affects the choice at t2. That would be the gradient of the policy at t2 with respect to the activity at time t. We then can multiply this together to get the total intermediation of this voxel in transferring the effect of reward from T1 to T2. In other words, how much of reward has flown into this voxel at time t. And we can calculate that for all the voxels in the brain and also for all time steps between T1 and T2 in order to get a 4-dimensional map for the contribution of each voxel at each point in time in decision making and learning. And we can show that if we sum over all the individual contributions of the voxels, here we can recover the behavioral effect that we introduced earlier. So these neural measure that we introduced here and this behavioral measure here are in fact two consistent measures with each other. Excuse me. As a typical scenario, let's assume that there was a choice here and subjects chose to press the bottom and they earn a reward as a consequence of that, and around 4 seconds later there is another choice point here. And the question is, which brain regions are involved in transferring the effect of reward in this period of time? So we looked at the brain regions that are in the top 1 percentile of the contribution, and we calculated a neural measure for them. It turned out that 3 brain regions are involved here: ventral striatum in blue, anterior cingulate cortex in green, and primary motor cortex in red here. And if we look at the activity of the brain at each point in time, we see that at the beginning, ventral striatum is online, this region here. This is a region that we know from previous literature is involved in calculating prediction error. But here we also see that the reward travels from ventral striatum to anterior cingulate cortex here, possibly for resolving the conflict between the actions. And finally, as we expect, the effect of reward travels to primary motor cortex for the final execution of the action or pressing the bottom. So in this way, we can recover which brain regions are involved in decision making, and also we can recover the temporal pattern of engagement at each point in time in reward processing. Just to summarize, we provided an end-to-end framework for analysis of decision-making circuitry in the brain. And for the next step, we believe that this kind of technique can open new doors into better understanding of the role of decision-making in different kinds of psychiatric disorders, and we are going to work more on data sets that involve patients with different kinds of psychiatric disorders. We have more quantitative results, and please come to my poster 102 for more results. Thank you very much.
So we have a couple of minutes for questions. If you have questions, please go to the mic and ask them. If not, then I have a couple of questions.
Yeah, I had a quick question. Hello?
Yeah, I think we can hear you.
Yeah, that was a really fascinating talk. I was curious though, why did the striatum start low and then increase over time? Shouldn't it actually be the opposite?
Yes, very good question. So you see here, on one side we have the probability of the hand movement, and on one side we have the probability of the isocard. Because the chosen action was the hand movement, we expect to get a negative effect at the end, and this is why the striatum started to be negative from the beginning. If the chosen action was the isocard, it would start from the positive at the beginning. This is arbitrary choice that we made to represent hand movement on the negative and the isocard as a positive effect. Thank you.
Hi, you said that you were going to do some work perhaps in the future on different, people with different psychological disorders,
Yeah.
See how their decision making has changed. Are you planning on doing things with other, if when people are impaired, their decision making is impaired by other things such as alcohol or other drugs? Are you going to do any research in that area?
Yes, probably. Currently, we don't have readily the data sets in the area of alcohol and drug abuse, but we have data sets for borderline personality disorder, depression, and bipolar disorders. That probably would be our focus for the next step.
Okay, thank you.
Thank you.
Is it possible that there are some regions of the brain that are important in the next decision, but have sort of saturated, so they're no longer sensitive to small changes in the reward? Did you consider, like, you think that's possible, and would using something other than a gradient maybe make sense there?
It's a very good question, very good question. We haven't considered that, but it's a possibility, and I think it would be very interesting to look at other techniques for interpreting networks that are not sensitive to these kind of saturations. But we haven't done anything yet on that front.
Hi. The temporal resolution of fMRI is not very good. Can this framework be applied to EEG data, and have you done that, or are you planning on doing that?
Yes, exactly. Very good question. That's another concern here. I think the same framework can be applied to EEG with some alterations. We haven't done anything in that front yet either, but I guess it's a very good point. Since EEG has a better temporal resolution, it might be a better candidate for applying these kind of techniques. Yes, exactly.
All right, let's thank our speaker. Thank you. We have a next a bunch of spotlights. The next one is Why is My Classifier Discriminatory by Irene Chen, Frederick Johansson, and David Sontag.
Hello, everyone. My name is Irene, and as Timnit mentioned, this is work done jointly with Frederick Johansson and David Sontag. When I first started my PhD, I was surprised by how easy it is to make a discriminatory algorithm, even unintentionally. As a project, I trained a classifier to predict hospital mortality from clinical notes in the intensive care unit. Better predictions would help doctors make better clinical decisions. Imagine my surprise then when my model showed different errors for different racial groups, with especially high errors for Asians. Why? Why would a classifier, and especially my classifier, be discriminatory? This paper seeks to answer that question. We analyze sources of unfairness by decomposing into bias, variance, and noise. We also demonstrate the effectiveness of methods to guide feature augmentation and data collection. There has been considerable work in the area of classification fairness recently, mainly focused on the model, using techniques like regularization or representation learning. But the data can also impact the classification fairness. Factors like sample size or features can impact the accuracy and therefore the fairness of the model. We argue for real-world applications, both the training data and the model should be considered. So why might a classifier? What are some reasons that a classifier might be unfair? Consider these data points. We have orange dots and we have blue dots, drawn from a generating data function. When we train a model, we can train one model, or we can use the group variable as input and train separate models. Either way, though, notice that the orange dots are underrepresented compared to the blue dots. Therefore, any model we learn will have higher error for orange dots than blue dots. We call this error from variance, and then would recommend collecting more samples. In another situation, here we have relatively equal numbers of orange dots and blue dots. If we learn one model or two models, we still see that the error for the orange dots is on average higher than the error for the blue dots. Because the orange dots come from a quadratic generating function, the linear model is ill-specified for the orange dots compared to the linear model of the blue dots. We call this error from bias, which could be solved by changing the model class. One last example, blue dots, orange dots. Here, no matter the model, our error on average is higher for orange dots than blue dots. Because the orange dots are simply harder to predict, no matter if we had infinite data or the best model possible, our error for orange dots is still higher. Error for noise, as we call it, could be solved then by collecting more features. So how do we define fairness mathematically? As I explained earlier, we define fairness in the context of loss. Loss could be false positive rate or accuracy, or other loss functions as well. Unfairness, then, is the difference between loss for two groups. Note that we rely on accurate Y labels. We can decompose any loss function into bias, variance, and noise, the three error terms that I outlined earlier. Unfairness, then, as the difference between loss functions, can be decomposed into the sum of the differences of bias, the differences in variance, and the differences in noise. Returning to our original example of predicting mortality from clinical notes, we are interested in how bias, variance, and noise then influence the differences in error by racial groups. When we subsample the data to simulate how adding additional data would increase accuracy, we see that error for all groups goes down. Great. However, we also can fit these learning curves using inverse power laws. The inverse power laws allow us to estimate the asymptote. The asymptote then represents the infinite data limit, or a world where there is no variance. No variance because of the infinite data. That relieves bias and variance. To address noise, we can also use topic modeling to find subpopulations that allow us to gather features in a constructive way to reduce noise. Looking forward, we hope that for accurate and fair models, both the data and the model should be considered. And in this paper, we show easily implementable fairness checks, which we hope will guide further efforts to reduce unfairness. Thank you, and we're in room, we've changed rooms, so we're in room 517 instead of 210 and 230. We're poster 120.
Our next spotlight is Human in the Loop Interpretability Prior by Isaac Lage, Andrew Ross, Samuel Greshman, Bing Kim, and Finale Doshi-Velas.
Hi everyone, my name is Ike Lage. I'm going to be talking about optimizing for interpretability with humans in the loop. Interpretability is one of the tools that we have available to us to make sure that when we use machine learning in the real world, we do so responsibly. But defining interpretability is hard, so how are we supposed to measure it? One direct way to measure interpretability is through user studies. But user studies are expensive. So a lot of prior work that optimizes for interpretability has taken an approach where they first choose a proxy for interpretability that can be evaluated computationally. This might be something like sparsity, for example. Then they optimize that proxy, finding a model that is, for example, sparse. And finally, they may choose to run a user study to evaluate whether the model they found is in fact interpretable. But this raises questions like, which proxy should I choose? And if I go through this whole process and I find that my model is not interpretable, how can I use those results to go back and actually choose a better proxy? So we follow a different approach that, to the best of our knowledge, we're the first to do, where we actually optimize for interpretability with humans in the loop. And so what this means is that we start with a model, we run a user study to determine how interpretable it is, and we actually use the results of the study to go back and directly update the model, making it more interpretable at each step. So we can view this as a Bayesian inference problem, where our goal is to bias the models we learn to be interpretable to humans. This requires us to first formulate a prior that encourages interpretability. So in this previous work, the step of choosing a proxy for interpretability can often take the form of defining a prior. But this again brings us back to the question of which prior captures the notion of interpretability that you care about. In our approach, we actually evaluate interpretability directly through user studies, and this evaluation is how we evaluate our prior. And then once we have this, we go about identifying the maximum a posteriori solution. So I'm not going to bore you with the details of exactly these terms in this talk, but I want to highlight two things. The first is that the likelihood is easy because we can evaluate it computationally. There are no users involved. But the prior is really hard, because to evaluate this, we need to run a user study. This motivates the key technical challenge that we address in our work, which is how can we approximate the map solution with few evaluations of this expensive prior. Our approach has 2 steps. In the first step, we identify a large collection of diverse, high likelihood models. We can do this because we know how to optimize likelihood, and while we don't know what makes a model interpretable, we have many hypotheses for what might. The idea here is that while we have not yet evaluated the prior for any of these models, some will have higher prior values than others, making them better approximations to the map solution. Then we go about finding these models that have high prior values and that are good approximations to the map using a combination of Bayesian optimization and user studies. This requires us to first define similarity between models, which we do based on features of the explanations. Then we choose a model and we run a user study. When we get the results back, we propagate them through the graph, allowing us to estimate the value of the prior in parts of the parameter space that we have not yet seen. Through these estimates, we choose the next model to evaluate. Again, propagating the results of that user study through the graph, allowing us to refine our estimates of which parts of the parameter space have high prior values. Eventually, evaluating models that do in fact have high prior values, making them good approximations to the map solution. So in this work, we present a framework for optimizing for interpretability directly using human feedback. Our approach is able to efficiently identify models that are both predictive and human interpretable. And we ran our approach on real data with real users and found that on different data sets, the map approximation it finds actually corresponds to different proxies for interpretability, suggesting that choosing your favorite interpretability proxy and optimizing it will not always be enough. For more, please come by my poster. It's number 119, and thank you for listening.
Our next spotlight is link prediction based on graph neural networks by Muhan Zhang and Yixin Chen.
Hello, everyone. I'm Muhan Zhang. It is joint work with my advisor, Yixin Chen. Given an incomplete network, link prediction is to predict whether 2 nodes are likely to have a link. It has many applications, such as friend recommendation, product recommendation, biological interaction prediction, knowledge graph completion, and so on. A main category of link prediction methods are heuristic methods. A heuristic method calculates a proximity score for each pair of nodes as their likelihood of having a link. There are many very simple but effective heuristics for link prediction. Let's see some representative ones. I will use gamma x to denote the neighbor set of node x in the graph. The first one, called common neighbors, predicts links by counting how many common neighbors x and y share. It is widely used in social network friend recommendation. The common neighbors heuristic is a first-order heuristic because we only need to know the one-hop neighbors of x and y to compute the score. The second one, preferential attachment heuristic, predicts links by the product of x and y's degrees. It assumes that x prefers to connect to y if y is popular. It's also first order. Now let's see a second order heuristic, the atomic ADAR heuristic. Basically, it is a weighted common neighbors, where a high degree common neighbor such as node A is weighted less than a low degree common neighbor such as node B. It assumes that both x and y connecting to A is not surprising because A also has many other connections. The AA heuristic is a second order heuristic because it involves up to 2 hop neighbors of x and y. Let's see some high order heuristics. The cuts index sums all the walks between x and y, where a longer walk is discounted more than a shorter walk. It is high order because one needs to search the entire network in order to find all the walks between x and y. Another popular high-order heuristic is the rooted page rank, which uses the stationary distribution at node y of a random walker who randomly returns to node x as the likelihood of link xy. It is also high-order heuristic. So generally speaking, high-order heuristics have better performance than first and second-order heuristics. Despite the success of heuristic methods, there are several drawbacks. Firstly, heuristic scores are handcrafted graph structure features. They are not able to capture the general graph structure features that might be useful for link prediction. Secondly, heuristic methods have strong assumptions on link formation mechanisms, thus only working well on certain networks. In this paper, we proposed a new link prediction framework, SEAL, which overcomes the above drawbacks by automatically learning general graph structure features based on a graph neural network. It achieves new state-of-the-art link prediction performance. Given a set of positive training links and negative training links, illustrated as link AB and CD in this figure, SEAL extracts a local neighborhood subgraph enclosing each training link. The local subgraph is then fed to a graph neural network to train a graph classification model. So why is classifying these subgraphs able to make link predictions? As we can see, if the subgraphs are large enough, we can accurately calculate all the first-order and second-order heuristics based merely on these subgraphs. Using a graph neural network, SEAL tries to learn such suitable heuristics. But the learned features are general. It does not rely on any predefined heuristics. But how about high-order heuristics? We know that high-order heuristics often have better performance at the cost of requiring the entire network. Does this mean that we need to extract the entire network in order to learn high-order heuristics? The answer is no. We developed a garm decaying heuristic theory to support it. Our main results are as follows. We proved that a wide range of high-order heuristics can be unified into a single garm decaying heuristic framework, including the CAS index, rooted page rank, sim rank, etc. This means that they intrinsically share the same form. We also proved that under mild assumptions, all garm decaying heuristics can be well approximated from local enclosing subgraphs, and the approximation error decreases exponentially. This means that we don't need the entire network to learn high-order heuristics, but often a small subgraph is enough. See you at poster number 121. The location on the slide is not correct. It will be in room 517 AB. Thank you.
Our next spotlight is Realistic Evaluation of Deep Semi-Supervised Learning Algorithms by Avital Oliver, Augustus Odena, Colin Raffel, Ekin Doge-Kubuk, and Ian Goodfellow.
Hi, my name is Colin. I'm going to be talking about our work on evaluating semi-supervised learning, and this is work with my friends Avital, Augustus, Doge, and Ian. So what should we do when we're training a classifier, but we only have a few labels? Is this a good decision boundary between the two classes? Or maybe this one? Or how about this one? Now, what if we also have access to unlabeled data? Semi-supervised learning methods leverage unlabeled data to learn a better classifier. These approaches have recently had a series of successes in performing reliable classification even when labeled data is scarce. Typically, these models are evaluated like so. First, we take a common labeled data set like MNIST, and we treat most of the data points as unlabeled. Then we train one classifier on only the labeled data and another classifier using the labeled and unlabeled data using semi-supervised learning. The semi-supervised learning technique is effective if it achieves higher accuracy than the fully supervised baseline. In our paper, we argue that this method of benchmarking fails to reflect many real-world settings. As a first step, we re-implemented various state-of-the-art semi-supervised learning algorithms and tested them on CFAR10 with 4,000 labels and SVHN with 1,000 labels. Variability in the underlying model and other implementation details can prevent direct comparison between different methods, so we created a unified framework for all of the algorithms. We used 1,000 rounds of automatic hyperparameter tuning for every method, including the fully supervised baseline. The first thing we noticed was that the gap between semi-supervised learning methods and the corresponding fully supervised baseline was smaller than generally reported. This is likely because we used the same budget for hyperparameter tuning for the semi-supervised learning methods and the baseline. Another baseline to compare semi-supervised learning against is transfer learning, which can obtain good performance on small labeled data sets by pre-training a model on a large related data set. This baseline is missing in most semi-supervised learning papers. We found that basic transfer learning from ImageNet to CFAR10 outperformed the best semi-supervised learning method we studied, even when we removed the classes from ImageNet which were similar to CFAR10 classes. Many papers only report semi-supervised learning results for one particular amount of labeled data. We evaluated each approach with varying amounts of labeled data and found a surprising variability in the performance of each method based on the number of labels available. Another issue with the way these algorithms are typically evaluated is that treating part of the labeled dataset as unlabeled results in a perfect matching between the classes in the labeled and unlabeled data. In some real-world scenarios, we can't guarantee that the labeled data has the exact same classes as the unlabeled data. To simulate this, we varied the amount of mismatch between classes in the labeled and unlabeled data and found the surprising result that performance of semi-supervised learning algorithms can actually become worse than the fully supervised baseline when there is class mismatch. As a final example, a common and particularly unusual practice is to continue using the standard validation set for a given data set even after discarding most of the labels in the training set. This can result in the validation set being many times larger than the number of labels in the training set. To test how much this actually matters, we computed the variance in validation error for different methods across different validation set sizes and found that for realistically small validation sets, it would be infeasible to reliably compare the performance of two methods or hyperparameter settings. Further discussion of these results and additional observations are available in our paper. We've released all of the code used in all of the experiments at the GitHub repository shown on the screen. If you have any questions or want to learn more, come see our poster number 95, all the way in the back of the room, at the poster session starting in about 5 minutes. Thank you.
Our last spotlight is automatic differentiation in ML, where we are and where we should be going, by Bart van Merenboer, who's presenting, Olivier Berlot, Arnaud Bergeron, and Pascal Lamblin.
Hello, everyone. My name is Bart, and I'm going to be presenting some of our recent work on automatic differentiation for machine learning frameworks. So our paper kind of has two parts to it. So we begin with a review of the way automatic differentiation is implemented in current-day machine learning frameworks. And we take different perspectives, such as systems programming, compiler design, programming languages, and of course, automatic differentiation theory. We argue that automatic differentiation affects the design choices in each of these different areas, so that any machine learning framework should be implemented from the ground up with automatic differentiation in mind. With this in mind, we propose a new prototype framework called MIA, which implements automatic differentiation in a different way than it's commonly done in machine learning frameworks. So to quickly review, there's two kind of current paradigms in machine learning frameworks that most people will be familiar with. On the left-hand side, we have a code snippet of TensorFlow. TensorFlow is a data flow programming framework, so it expects the user to explicitly construct a data flow graph. Automatic differentiation is then expressed as a graph transformation, like a transformation of this graph, which is then executed in a custom runtime. On the right-hand side, we have an example of a framework called AutoGrad. AutoGrad uses a technique called operator overloading. This means that it executes a plain Python function, but all the numerical operations are overloaded so that they are tracked and stored on a tape. And at the end of the execution of the function, the derivative can be calculated by walking this tape in reverse. Now, these two frameworks have a very different set of advantages and disadvantages. For operator overloading, there's significant runtime overhead in some cases, because at runtime, each numerical operation has to be traced, has to be stored on a tape, and at the end of the execution, this tape is this data structure that needs to be walked in reverse. This needs to happen each time the function is executed. On the other hand, for data flow programming frameworks, all of this is done ahead of time, which means that there's no runtime overhead. In operator overloading frameworks, we bind ourselves to the host language, so in this case, Python. This can be problematic if the host language is relatively slow, as is the case in Python, and doesn't allow for a lot of optimization. On the other hand, if we have a data flow programming paradigm like TensorFlow, there's a custom runtime and a custom compiler which can very aggressively compile and optimize our numerical code. The big advantages, though, of operator overloading are that the end user can write plain Python as opposed to explicitly constructing this computation graph. This is a lot more user-friendly. On the other hand, because the user is writing plain Python and operator overloading only cares about tracing the numerical operations, it means that they can use all the features available to them in the host language. So think about things like object-oriented programming, higher-order functions, recursion, etc. None of these things aren't necessarily available in a data flow programming paradigm because the user is limited to the operators that are implemented in this data flow graph, and those are normally far fewer than available in a general programming language. In MIA, we take a different approach to implementing automatic differentiation directly into the compiler. This means that it represents an entirely different set of trade-offs, which we think kind of combines the best of both worlds. MIA parses a subset of Python code into a newly designed graph-based compiler representation, which is based on a normal form that's commonly used in functional languages. It then applies automatic differentiation on this graph-based representation by constructing a series of closures instead of using a tape. This makes it much easier for the compiler to jointly optimize the forward and backward pass, something that's generally not possible in operator overloading frameworks. This graph representation, though, is far more functional than the common data flow programming graphs in a sense that it can represent recursion, it can represent higher order functions, and it can represent closures, none of which are usually possible in the data flow frameworks that we use. Please come see us at our poster, number 94 in room 210 to talk more about automatic differentiation for machine learning frameworks, and thank you for listening.
See you at the poster session.